Welcome back. Now that we have completed Unit 1, we'll take a look at Unit 2. So rather than simply focusing on the math necessary for us to do chemistry, we're actually going to get into some terminology, some definitions that we can work with, and then we're going to move back into the more analytical side here shortly. But Unit 2 is going to introduce some concepts for us to work with. Chemistry is the study of matter, so what is matter? What are we actually attempting to study this year? It's simply anything that takes up space and has a mass. So solids, liquids, gases, other states of matter, but it's got to have a mass to it and it needs to take up space. Okay, so some of the common questions are what's not matter, right? Most frequently, like what are we looking for? What is not matter? And mostly the answer for us is energy or forms of energy, heat, light, sound, things like that. That is not matter, okay? But it's got to take up space. It has to have a volume and a mass. For this section, what we are covering specifically are called pure substances, meaning that it's a substance that is just that substance with nothing else mixed in with it. It's got uniform composition and an unchanging composition, so it's same all the way throughout, right? That's what a uniform is. Some of you might have had a uniform in middle school or grade school, right? We have a dress code, but when it means uniform, that means the same all the way throughout. Okay, so these substances are the same all the way throughout is what we're talking about here today. So we're going to go through states of matter. Now I know most of you could probably give me plenty of examples if I asked you what is a solid. You could point at something and tell me that it's a solid. But actually coming up with a definition of what it is a little bit trickier. And so what you need to do is think about it in terms of what happens when you put matter into a container. That's going to dictate sort of how we define what it is. And so for us, a solid is a form of matter that has its own shape and volume. Okay, that if you put it into a container, it doesn't magically transform into the shape of the container. It keeps its own shape. Sometimes it's called definite. Okay, that it's definite shape and volume, meaning that it doesn't change based on the container. The particles in solids are tightly packed together, as you can see down here. Probably not a bad idea to kind of sketch that particular drawing in your notebook into these repeating and regular patterns. Here you can kind of see it's sort of cubic in shape. It's not always necessarily a cube, but there's some sort of repeating pattern for most solids, at least for the solids that we're going to deal with. Okay, and this pattern is called crystalline structure for the adjective for crystal, or we'll hear it called a lattice, like the word lettuce, but just with an A, lattice. Lattice structure, crystalline structure. Okay, that is the three-dimensional shape that this thing is going to work itself into. Okay, so solids, when you heat them up, will expand, but expand ever so slightly. So if we think back to what temperature was in the first unit, right? The average measurement of a substance's kinetic energy, how much it's moving, right? So what happens when you heat stuff is that it will move a little bit faster, right? Back and forth, faster and faster in place. So even though they're locked in this sort of lattice position, they can wiggle around a little bit more. So as you start to heat up a solid, right, if you were to heat up this rock, what happens is these particles move back and forth more and more. They take up a little bit more space, so they will expand slightly when heated. If any of you have a metal door at home, or at maybe if you have a job, most doors, right, they fit nicely within the frame here. If this is the edge of my door and this is my frame, there's usually a tiny amount of space in between them, right? But if you have a metal door in the summer, what will happen is that door will slightly expand, okay, and instead of being, that close, it'll maybe be, this close, and it gets harder to shut that door. Sometimes the edges will stick, and the opposite will happen in winter. It will slightly contract, and then you have to worry about, is this thing going to latch, right, where the handle is. But the doors will expand slightly, and sometimes they're hard to open and close in the summer because they'll start sticking to the frame. Okay, so a solid, right, has its own shape and volume, a definite shape and volume. So how is that different than a liquid? Again, most of you could give me examples of liquids, but how do you actually define it? Again, think about what happens when you put it into a container. It's a form of matter that flows, has constant volume, and takes the shape of its container. So the volume is constant. It doesn't expand to fill the container. It just fills whatever the volume of the liquid is. It does take the shape of the container, and it flows. So what happens, right, with solids, okay, once you heat them up enough or they have enough energy, they'll break out of that lattice structure. Right, you give them enough energy, those particles will eventually break out of that structure, and we get into liquids. This is what happens when ice melts. Okay, those particles that were locked into position are now free to kind of tumble over each other. Notice they are still in contact. All right. Okay, and again, I would draw these little boxes here in your notes. Notice they're still in contact, right? But they're not locked into position anymore. They're not rigidly held in place. So that's your difference between a solid and a liquid, right? These have a bit more energy to them. They're not stuck in those positions, okay, that lattice structure. Generally, liquids are less packed than solids, meaning they're less dense. The notable exception there is water, of course, right? Ice floats in liquid water. That's the one major exception. Unfortunately, it's a very common one, so it might lead you to think otherwise. But generally, solids are more dense, right? They will sink, okay, in their liquids. So what happens here, right? The particles are able to sort of move past each other. They take the shape of the container but don't necessarily fill it. They only fill however much of the liquid there is, right? If there's only half of this container, it's only going to fill half, okay? Kind of like solids, liquids will expand when heated ever so slightly, right? These particles will move faster and faster, and they'll start to take up a little bit more space. Eventually, if you give these things enough energy, they will actually break away from each other, right? So step one was kind of breaking that crystal structure. And step two is breaking the attraction between particles here so that these particles all come apart. And that's where we get our third state of matter. Okay, so gases are a form of matter that not just flows, but also conforms to the shape of its container and fills the entire volume of its container. Okay, so unlike liquids, right, this will expand to fill the entire volume of the container no matter how much you have of it. So what happens? Well, with gases, right, once again, I would, draw these boxes of what's in here. With gases, they're going to take up a lot of space. You've given these things enough, okay, energy now that they will actually, come apart. These things are flying around. They basically keep going in a straight line until they hit the walls of their container or another particle. All right, they're moving pretty fast. Some of them up to upwards of a couple hundred meters per second. As you're just sitting in the room there, these particles are colliding with you. You don't really notice it because they're very light. But if you get enough of them on a blustery, like windy day, right, you'll feel the wind blowing you back, right? You know it's there. So these particles are very far apart. The other thing to note here, and it got cut off this line here with this picture, is that gases are compressible. Right, with all that space in between particles here, okay, theoretically you could take this thing and squeeze it right in all three of its dimensions, squeeze it down, and you can compress the gas, okay? We do this all the time with things, right? We get containers full of gas, a scuba tank's full of oxygen gas. If you've ever worked in the food industry, you have carbon dioxide canisters that you hook up to a soda fountain so that the liquids come out bubbly, right, with the carbon dioxide. Okay, so those are what you're doing is you're just taking the gas and compressing it. If you didn't compress it, it would take up too much space, right? So you compress it so it takes up less space. It's easier to ship it, to make it, right, to take it to places. It's easier to handle. So gases are compressible. Solids and liquids kind of are. But if you start, it takes a lot of pressure to do that, and pretty quickly, if you start applying a pressure to solids and liquids, you get some funny things happening. Okay, but gases are compressible. I am going to add this one into your notes. It's not listed on our main three, but it is a fourth state of matter. It's actually the most common state of matter in the universe, and that is plasma. It's the most common in the entire world. We don't really see it here on Earth, and that's because it is in stars, right? So the question becomes, right, most guys ask, like, what happens if I keep heating up a gas, right? We talked about when you heat up a solid, right? The lattice structure breaks down. When you start heating up a liquid, the particles separate, they come apart, right, and they turn into gases. Well, what happens if you keep heating up a gas, right? What if you keep adding energy to it? What's sort of the next step? and you'll reach this state eventually where it turns into plasma. And what that is, it's basically a gas or gases that are stripped of their electrons. Basically, and we haven't talked about electrons yet, but we will here soon enough, is that you heat it up enough that the atoms themselves start to come apart. And so it's stripped of their electrons, and you basically have all these nuclei bouncing around at very high energy levels, colliding and fusing. Okay, that lets off a lot of heat and light as a byproduct, right? And we get that here on Earth as sunlight. Okay, but this is the most common state of matter in the universe because all stars are made out of plasma. There are other states of matter other than these four, but they exist under some really extreme conditions. An interesting one, if you want to Google kind of a cool, see if you can find a YouTube video on it. A cool thing is called a superfluid. It's a fluid that has no resistance to flow. It'll actually climb up the walls of containers by itself. It's really interesting. But it only happens with really helium close to 0 Kelvin. It's pretty darn close to 0 Kelvin, and like I forget what the pressure is, but a pretty high pressure. Okay, an unnaturally high pressure. So there's all kinds of these interesting states of matter, but they exist in these very extreme conditions. Ones that we don't generally obviously encounter here on Earth. So finding them, discovering them, and having practical purposes of them, it's a little bit hard for us to do that. But there's, I don't know, probably hundreds, if not thousands, of these other types of states of matter that we don't commonly see here on Earth. Okay, enough about states of matter. Let's talk about the properties of matter. There's two types. We've got physical, okay, and then we've got chemical. And under the physical branch, we have extensive and intensive. Okay, and we'll talk about what the difference of those are here in just a moment. But we've got physical and chemical, okay, properties. So what's a physical property? This is a characteristic of matter that can be observed or measured without changing the sample's composition. So these are unique to each substance. It's right, this substance by itself, not how it behaves in the presence of other things. It's just how does this thing behave by itself. Okay. These are, again, we're describing pure substances, not a mixture of substances. So examples here: density, color, odor, hardness, melting point, boiling point. I think that got cut off, right? You do not need to obviously copy this table. This is just kind of some points for you to take a look at for physical properties. But right, oxygen, mercury, water, sucrose, sodium chloride. The first two are elements. The bottom three are compounds. Right, we see different colors. Okay. State of matter at 25 degrees Celsius, the melting point, the boiling point, and the density. You might also note here, right, sucrose doesn't even have a boiling point. What happens is after 186 degrees Celsius, eventually if you keep heating it, it decomposes. It stops being sucrose and actually comes apart into its constituent parts. So if you've ever, sucrose, by the way, is table sugar. If you've ever burned sugar on the stovetop, right, you're not really burning it. What you're doing is you've reached a point past its melting point, but before it is boiling, where you actually are like caramelizing it. It actually burns. Kind of smells really bad if you ever burn sugar. It's not a pleasant smell. Right. What ends up happening is stuff starts to decompose with enough heat. Okay. But physical properties describe the substance by itself, not how it behaves in the presence of other things. Under the umbrella of physical properties, okay, we will have extensive properties and intensive properties. Extensive properties are ones that are dependent on the amount of substance present. So if the particular thing you're measuring changes, then the extensive property of that thing changes. So that would be like mass, length, volume. Okay, if you add more of a substance, it's going to gain more mass. If you add more of a substance, it's going to take up more space. Right, it's going to have a larger volume. Okay, so those are extensive properties, properties that change based on the amount of substance present. The other type here is intensive, and these are independent of the amount of substance present, where it doesn't matter how much you have of it. A classic example here is density. You might think back to that lab that we did with the unknown. I gave you, 3 metal blocks, and one of them you might remember was, or if you did your math right, was aluminum, which had a density of 2.70 grams per cubic centimeter. And Later on in that same lab, I gave you a piece of aluminum foil, and I said, figure out how thick this is. And part of figuring that out was realizing that the density of that piece of aluminum foil was 2.70 grams per cubic centimeter. It didn't matter what shape it was, right? It was much thinner, it was much lighter than that metal block that I gave you, but it has the same density, right? It doesn't matter how much you have of it or what shape it's in. That's always going to be the same. Some other ones there: boiling point, melting point. Those are other examples of intensive properties. These two oftentimes trip students up, especially things like boiling point. So when you think about, like, say you got two containers of water on the stovetop and you're heating them up, and one is a saucepan with a quarter cup of water in it, and another one is a big pot for boiling noodles and it's got 6 quarts of water in it. And most guys will go, well, yeah, the one with the less water is going to boil faster. So therefore, boiling point does matter how much you have of the substance. The reality is it doesn't, because they both boil at, right, if we're talking about Celsius here, they'd be both boiling at 100 degrees Celsius. It doesn't matter how much you have, whether it's a little amount of substance or a lot, right? Okay, a big pot full of water or just a little saucepan of water. They're both going to boil at 100 degrees Celsius. The reality is there's less of this to boil off, but the temperature didn't change that it boils. So just kind of keep that in mind, right? So I point this one out because oftentimes guys get confused on that, but it's the temperature, not how long it takes for it to boil. Okay, so extensive changes based on how much you have. Intensive stays the same based on how much you have. Other ones here, right, on intensive, just to throw them down here: color, right, odor. Doesn't matter how much you have it. Odor might get a little bit stronger, but the actual smell doesn't change, right? What it smells like doesn't change. And the last one here, the first part of the day, is chemical properties. So we talked about physical with extensive and intensive. Chemical properties, okay, are talking about the ability or inability of a substance to combine with or change into one or more other substances. So this is how it behaves in the presence of other things. Good example here, this is copper oxidizing. I know this got cut off a little bit. Okay, copper oxidizing. So what happened with the Statue of Liberty? Well, when the French sent this thing over to us, it was a copper statue. It looked like a giant penny, right? That's kind of what it looked like, okay? Something like this. But if you know anything about copper, over time, copper will rust or oxidize, right, is our chemistry term here. It reacts with oxygen in the atmosphere and it begins to rust. And so we end up with this green that we've got today, right, that outer layer of copper all oxidized, okay? So that's just a chemical property of it, right? Copper will react with oxygen to form a copper oxide rust. Another thing that happens is that in environments with high humidity, this process is accelerated. Well, we stuck this thing in a harbor, right? It's up in New York City if you've ever seen it, but it's basically sitting in the harbor in New York City, so there's a lot of humidity in the air. So this process sped up quite a bit. Probably within, I don't know, the first 15 to 20 years of this thing sitting in the harbor, it went from the bright, shiny copper to the green color that it is today. Okay, so just kind of a cool fact about it if you didn't know what it used to look like, right? That's what it at one point in time did look like. This is obviously a colorized picture, right? There wasn't color photos back when they gifted this thing to us. The second part of the day here, we will talk about sort of the history of chemical thought. What did like historian or people in history say about chemistry? How did it become a science? What was the sort of pathway that got us to where we are today? I think this stuff is kind of interesting as at least a thought experiment as how we got to where we got to. So, how did we start talking about chemistry, right? The study of matter. Well, early in history, right, early peoples weren't able to really spend their time thinking about the bigger questions of life, right? They're more worried about, where's my next meal coming from? Am I going to get attacked or mauled, in the evening or when I'm sleeping? They were more worried about, right, the practical things. But once we started getting societies that showed up, they started asking the bigger questions of, what is all this stuff? And so the first people to at least write it down, to have some sort of record of it, were the ancient Greeks. And they said that matter was one of 4 things: earth, water, air, or fire. There's a 5th one, ether, which is what came from the gods, but it's not what would have been on earth. Okay, so everything that was a solid material was earth, right? You, a rock, dirt, trees, okay, whatever, that was considered earth. Anything that was liquid was some type of water, right? Anything that you're breathing in, right, that's blowing you over, that was air. And then obviously anything with energy or heat was fire. And I mean, that makes sense. At least they, tried to come up with an explanation for what this stuff is. Part of their understanding of these four things, though, is that matter was infinitely divisible. That is, that you could keep cutting it in half and cutting it in half, right? Okay, so if you start with some piece of material, you cut it in half, and you could cut it in half again and again and again and again and again and again and again, right? So on and so forth, all the way down. And you'd never stop, right? You could infinitely just keep cutting this thing. So that was kind of what the beginnings of chemical thought were, right? What is this stuff? What is matter? The first person to kind of have sort of an opposite idea of this was a Greek philosopher, Democritus. Lived about 400 years or so before Jesus, right? 460 to 370 BC. He's a Greek philosopher. Note, not a scientist, right? Okay, this guy does not have, right, any sort of science background. He is not a scientist. He is just a philosopher, but he's got good logic. Or he's a Greek philosopher. He proposed the idea that matter was not infinitely divisible, that there was some point, as if when you keep cutting this thing down in half, where you can no longer cut anymore. And his logic was that eventually, at some point, the tool that you're using to cut with is going to be too wide, right? It'll be so wide that you can't cut the piece down there. So if that's the case, right, then how are you going to keep cutting it down, right? What are you going to do? Take this piece and cut it with itself? Right? No. So there was some point, logically, at least to him, that we couldn't keep cutting anymore because the tool we would use to cut down the material would be too wide to cut. Okay? And he called this point, whatever that was, whatever our final cutting point was, whatever was left were called atomos, which is the Greek word for indivisible. And that's where we get our, obviously, modern day word for atom, atomos, which means indivisible. So this was the first, again, not a scientist, just philosopher, thinker, right? This is a thought experiment that he did, right, with the cutting stuff down, and at some point we can't cut anymore. Not a scientist, but was kind of on the right track here and came up with this idea of atomos. Okay, so Democritus has his ideas of atomos, and matter is does reach a point where you can't cut it down anymore. Where do we go from there? Well, almost immediately, another guy, much more popular in history, Aristotle, comes around and he rejects this idea because he believes that empty space doesn't exist. He believes that matter is just one continuous sort of gelatinous sort of substance, right, that you just kind of drift through. That there's not empty space. Well, there is empty space. That does exist. So he's wrong on this. But he says that empty space doesn't exist. Therefore, Democritus's idea of this actually, point where we can't cut down anymore must be wrong. And if you note the date on this, right, this was, roughly, I don't know, he probably did this about 350 BC or so. Right, of the two guys, Democritus or Aristotle, right, he's the one who's more famous in history, right, Aristotle. So his idea is the one that's going to stick, and it sticks for a very long time, right? This is 350 BC. It is not until almost, right, the late 1700s, early 1800s before anybody else really kind of comes up with a radical idea to challenge this, right? So we're talking about the entire Roman Empire is going to come and go. Right, Jesus is going to show up on the timeline. All the Middle Ages are going to pass. The Crusades, right? The Renaissance, and even the Renaissance, which had a lot of really good scientific thinkers. Nobody is able to really break out of this idea of Aristotle, right, and saying that matter is infinitely divisible. It's not until the late 1700s with this guy where somebody finally actually challenges this. It's 2,000 years later, right? It's a long time with no advancement. Now we had stuff in the in the middle there. We had things where people try to do things like alchemy, which really isn't a science, right? We had people trying to do that. It's not really chemistry. It wasn't really studying matter. It was just attempts to turn stuff really into gold so that people can make money off of it. We wind up at John Dalton. And he's an English school teacher. Not that he teaches English, though I'm sure he did. This is meaning that he was in England, probably taught, middle school, grade school, maybe high school, but he was a school teacher. And Dalton was kind of like a backyard scientist by all accounts. And my guess is that if he were alive today, he'd probably have his own hobbyist YouTube channel of him showing off some of the cool experiments he's doing in his backyard. But John Dalton, in part of his experiments, starts to realize that compounds that he could form in his backyard had specific ratios that these things reacted. So, for instance, right, if he was trying to determine, the formula for water, right, which was H2O, and he realizes, right, for instance, in something like water, that there's 2 parts of hydrogen for every 1 part of oxygen, and well, if that's the case, then these things must have some sort of point where they're indivisible, because it seems to be reacting in a specific ratio. And if what Aristotle was saying was true, that matter was just all one giant continuous blob, it really shouldn't matter what the formula for this is, because it should just combine in whatever I make it combine with, not a specific ratio. So this leads Dalton to think that there is some point at which we can't cut things down anymore. And so he's going to push back on Aristotle and propose what he calls the atomic theory, which we'll see here on the next slide, which is really important. Which is going to be 1803, right? Almost 2,000 something years later before we get any real advancement in this. Okay, so before you go too much further, I would pause this and write these points down. These are future quiz or test question, I can promise you that. The points of John Dalton's theory, atomic theory, which he proposes in 1803. So what are they? He says that matter is composed of extremely small particles called atoms. Atoms are indivisible and indestructible. Atoms of a given element are identical in size, mass, and chemical properties. Atoms of a specific element are different from those of another element. Different atoms combine in simple whole number ratios to form compounds. In a chemical reaction, atoms are separated, combined, or rearranged. Okay, so these are the 6 points that he's going to write down. We'll kind of go through them here piece by piece. So matter is composed of extremely small particles called atoms. We still know that is true today, right? We still call those atoms. Atoms are indivisible and indestructible, meaning, so for him, right, we couldn't destroy them, we couldn't cut them down anymore. Now it turns out, with the right technology, we can actually do both of those things, but there's no way he could have known that in 1803. So he missed that one. I mean, he was correct in his time, but later on we'd find out that atoms are divisible, right? We know about protons, neutrons, and electrons, and they are destructible, right? Destroying matter is atomic bombs, okay? But this is what he said, right? He said that atoms are indivisible and indestructible. Atoms of a given element are identical in size, mass, and chemical properties. So, an atom of nitrogen and another atom of nitrogen, they're the same in size, mass, and chemical properties, is what he says. What actually is the case is they are the same in size, they are the same in chemical properties, they're not identical in mass, which he, again, wouldn't have known. But he came pretty close for not having any idea of what's really going on. He also says that atoms of a specific element are different from those of another element, meaning that nitrogen atoms will never suddenly start to behave like oxygen atoms. They are just all nitrogen or all oxygen, right? Each thing behaves like its particular element and not something else. That's still true, right? That's all 100% true. Different atoms combine in simple whole number ratios to form compounds. Yep, that's still the case. In a chemical reaction, atoms are separated, combined, or rearranged. Also checks out. So, for being 1803, which is a little over 200 years ago, this guy got really darn close to being what we know today to be true. And in his time, got as much true as he possibly could have known, which is really impressive. But definitely know this. This is a future quiz or test question. Okay, what are the parts of Dalton's theory? So just a heads up there. This is the last slide, and then we'll do a problem off of your homework together. So Dalton's theory leads to the quick acceptance of the law of conservation of mass. And you might remember from your time in biology, there's not a lot of laws that show up in science. And when they do, it's because they're really important, and they've got some sort of fundamental equation or some sort of fundamental fact about them that are it's a law of nature, right? And we don't get a whole lot of those. But Dalton's work led to this acceptance very quickly. And so what is conservation of mass, law of conservation of mass? It's that in any process, okay, such as like a chemical reaction, mass is conserved, meaning we don't destroy it, we don't create it. What we start with is what we end with. It's not conservation in the sense of like ecological conservation. It's conservation in the sense that it's not changed. Okay, so mass is not changed. So in chemical reactions, it means that mass is conserved by either separation, combination, rearrangement. Atoms have to go somewhere. We can't just create or destroy them. They have to come from something, they have to go to something. So Dalton's work led to the acceptance of this law that, right, whatever mass we start with, and this is what we're going to see here in just a moment, whatever mass that we start with has to equal the mass that we end with. And if it looks like something's disappeared, it's probably because we've produced a gas, right? Or if something suddenly got heavier, well, then it reacted with a gas, right? Because you can't see that. But the mass that you start with has to equal the mass that you end with. Okay, let's look at this one off of your homework. So this is for the worksheet part of your assignment. There's also a mastering assignment for you to work on. So this is part of the law of conservation of mass, right? And we said at the end of the last slide that the mass that you start with must equal the mass that you end with, okay? So it's helpful to identify when reading these problems what are the substances you are starting with and what are the substances you are ending with, and then setting them up and make them equal to each other. So in this problem, 152 grams of octane react with 240 grams of oxygen gas to form 275 grams of carbon dioxide and some amount of water. What's the mass of water produced in the reaction? So let's figure out what we are starting with. So we're starting with 152 grams of octane. We'll just label that S for starting. React with 240 grams of oxygen. We'll call that also another starting thing. To form, right, that seems to be indicating that we're making something. Carbon dioxide and some amount of water. So we'll label those both E's for what we end with. So now we're just going to set this up like a math equation. Okay, so we're going to set this up as, right, the mass that we start with, okay, has to equal the mass that we end with. And we are starting with, right, the mass of octane plus the mass of oxygen has got to equal the mass of carbon dioxide, we're going to label that CO2 to save some space, plus the mass of water. And then we're just basically making a simple algebra problem. Mass of octane is 152 grams. The mass of oxygen, so plus mass of oxygen, which is 240 grams, don't forget that decimal point, that is important, equals the mass of carbon dioxide, 275 grams, plus the mass of water. Well, I don't know that. That's, right, your variable x. We add up the left side. 392 grams equals 275 grams plus x. Right? X is going to equal, now to the right number of significant figures, we are going to the ones place here. Okay? And our unit, of course, is grams. So when we're writing an answer, make sure it's got the significant figures and the proper unit. Right? This one goes to the ones place. This one, because of the decimal, goes to the ones place. This one goes to the ones place. And this is addition subtraction rule. So whichever one goes the least far to the right is as far to the right as you go in your answer. Well, they all go to the ones place, so your answer should go to the ones place. Don't assume that, right, it's always two things on one side and two things on the other. Sometimes it's two things here and one thing over here, or one thing here and three things over here. You have to read the problem to figure out how many things you have on each side, okay? And as far as work goes, all right, you should definitely at least show your initial setup. You don't maybe have to show every single step in between, but you should at least show me your initial setup in addition to your answer. Don't just write, 117 grams. It shows me you just all you did was just either look at somebody's or write down the bare minimum here, right? I need you to actually show me that you can logically follow all that. And while this might seem super easy right now, right, we're playing Madden on rookie mode, right, where every play is going to get you positive yards. We're going to very quickly, okay, up the difficulty of this in the next few weeks. But we're starting off with, again, easy stuff. So that'll hopefully get you started there. So got two things to work on, this worksheet and then the mastering assignment. So take care of those two things.